देखिए जॉइन करना चाहिए
Am I audible?
Yes, sir, you are audible. So, hi everyone. The next lecture is of fundamentals of nanoscale MOS devices and circuits, and it is going to be taken by Professor Subhendu Kumar. So, I will give a quick introduction of Professor before starting today's lecture. So, Professor Subhendu Kumar received MTech degree in radio physics and electronics from University of Calcutta in 2001. He then joined Siliguri Institute of Technology (SIT), Siliguri, Darjeeling, India, as a faculty member. From 2005, he started working towards his PhD degree from Institute of Radio Physics and Electronics, University of Calcutta. He completed his PhD in 2009. Then he joined IIT ISM, India, in July 2009, and is currently serving as a professor in the Department of Electronics Engineering. Dr. Kumar was the recipient of the University Gold Medal in 1999. He is one of the 22 successful candidates to showcase his work at the 23rd IIS Colophon for Young Physicists YPC 2000, held at Saha Institute of Nuclear Physics, Kolkata. He received special appreciation from IIT ISM Dhanbad for excellent teaching and student feedback for the number of academic sessions. He is the fellow of IEEE India, senior member of IEEE Electron Device Society, IEEE Photonic Society, and a life member of Semiconductor Society of India and Materials Research Society of India, MRSI. He is an active reviewer for different journals, including Journal of Chemical Physics, IEEE Electron Device, IEEE Transactions on Nanotechnology, and other SCI journals. He was also one of the 2015 EDL IEEE Golden Reviewers. Apart from being a resource person for NEP 2020 orientation and sensitization program organized by the UGC Maldiya Mission Teacher Training Center, University Grant Commission UGC, Government of India, Dr. Kumar has been instrumental in organizing various national and international meets in various capacities. His current research includes optical properties of 3 to 5 nanostructures, low-dimensional MOS devices and related circuits, and interconnects for silicon and post-silicon era. Thank you so much, sir. So, please start your lecture.
Okay, thank you for the nice introduction. So first, let me try to share my slides.
Click on the share button. Beside the red leaf button, there is a share button.
Yes, will I share the window or the entire screen?
So the entire screen. It is visible, sir.
It's okay?
Yes, sir.
Can you see the full screen?
Yes, sir.
Okay. Can you see the pointer?
Yes, sir.
Okay, fine. So first of all, I want to thank Professor Rajiv for inviting me to give a presentation in this GAN course. And basically, I am aware of the theme of the course, but anyway or the round, I preferred to choose this topic of nanoscale MOS devices and circuits because anyway or the round, you see your background electronics, whether you use your memristor and all these things. And as far as the packing density is concerned, you need to reduce the size of the device. So conventional devices and non-conventional devices will definitely come into play when you speak about uh, any electronics. So I have classified my presentation according to this one. So first I will speak about something about the evolution of semiconductor devices and MOS structures. Then I will come to a little bit of conventional MOS and CMOS devices. And then the majority which I will focus, that is the need for scaling, and where we will see some non-classical or non-conventional devices. And thereafter, we'll have a discussion on few properties like variability, source and drain series resistance. And finally, we will end with something about interconnects. So to start with, in fact, I show this slide to many of my presentations. So, it started with some mechanical gears, and then it came to the Babbage difference engine. And finally, what you have, the whole computation in your wristwatch. So it's a matter of VLSI, very large scale integration. The previous definition of VLSI was integrating millions of transistors. Now it is the millions has changed to billion. So not even this wristwatch, you can find your computation in a ring. So basically what the semiconductor industry has seen there are two major inventions and one predictions, which is basically driving the semiconductor industry. The first one in 1947, the invention of point contact transistors. You can see. And another invention, a groundbreaking invention, was the invention of integrated circuit, monolithic integrated circuit by Jack Kilby. So these are the two things which governed, rather, which showed a roadmap for the semiconductor industry. And later on, what we can see, these are the various developments year-wise. And finally, what it has come to nanosheets or gate-all-around transistors. So this is a part which this is a part of my classroom teaching also, where I don't prefer to miss this slide, which is basically we spoke about two inventions, and this was the prediction by Jordan Moore. So in 1965, Moore published a paper in the 35th anniversary of the journal, which is called Electronics. And after observing for a couple of years, starting from the first commercial planar transistor in 1959 and till 1965, what he observed that the number of components per chip, that was doubling every year. And this was the first observation made by Jordan Moore. And Jordan Moore uh, mentioned about components. Now, components, it is basically the resistor, capacitors, and transistors. And definitely in our digital age, uh, the components have been converted to transistor counts, because all the registers and passive components that can be realized with the help of transistors. Now in 1975, Moore visited his law, revisited, I should say. And what he found that the industry is already slower. For example, a CCD memory, which had 32 components, the actual prediction was 65,000 components. So it was off by a factor of 2. So the second observation of Moore is, rather he observed that the number of components per chip will double every 2 years. Now, there are few technical drivers which can be considered as far as the complexity of circuits are concerned. The first is that you can increase the chip area, you can decrease the feature size, fitting more and more components in a chip, increasing the packing density. And that these two things will give you eventually 50% of your expectations. The rest remains the cleverness which has been adopted by the industry. There is no rule. That is the state of the art design, which we will see at a later stage. So from this observation, now Moore never said that this is a law. It is the industry, in order to honor Moore's observation, it was taken by a law and referred to as Moore's law, which states that doubling of transistor counts per every 18 months. And this became accepted. Although in the recent year, there are speculations regarding whether the Moore's law is followed or not. And traditionally, digital chips, it maintained the Moore's law as compared to analog chips. So now we go into a discussion on conventional MOS and CMOS devices. So the first thing is that in the age of VLSI, although it's not a age of VLSI, now it is an age of nanoelectronics, a bipolar junction transistor, is it a suitable candidate? So the answer for this is that if you want to maintain a packing density, then the BJT is not a suitable structure. Because, you know, if you look into the structure of a BJT, then you will be having two junctions. And each of these junctions will offer a depletion region. Now, reducing the size of the device, that is the essence of VLSI, that will, if you reduce the base region, then there is a chance that the two depletion regions, they will touch each other. And eventually, the BJT will lose its property. So, a MOS is always a better choice than BJT as far as VLSI is concerned. So what we have here, sorry, as far as the structure of a MOSFET is concerned, a planar MOSFET, we have the source, drain, and this is the gate region. So metal oxide semiconductor. So this part, this is the metal, this is the oxide, which was traditionally silicon dioxide, and you have the semiconductor, which is either P or N, depending upon what type of channel you need. Now, mind it, in fact, I am restricting my discussion to silicon, because what I believe is that although apart from silicon, there are many materials which which are coming, reports are coming, fascinating reports are coming from various materials, particularly 2D materials. But as far my experience and understanding goes, the market will not eventually sacrifice silicon for the next maybe 15 to 20 years. There are various reasons for that. So anyway, all around, so as far as the gate material is concerned, traditionally we used polysilicon. So it is a polycrystalline nature of silicon. And polycrystalline and interestingly, the body which you see here, this is the substrate. This is a single crystal. So a single crystal looks something like this. A polysilicon, it looks something like this. There are various grains, boundaries, and inside a grain boundaries, the atoms, they are aligned in a specific manner like that of a crystal. So traditionally, this polysilicon was used. And furthermore, this which you see here, this is the interface between the semiconductor and the oxide region. And depending upon the type of oxide, the quality of oxide, there will be a presence of interface trap charges. And these interface trap charges, they are responsible for varying the threshold voltages. And if you speak about the lattice or the Miller indices of the substrate, so traditionally for BJT it was a 111 plane, and for MOSFET it was eventually a 100 plane. Because a 100 plane, it offered less number of silicon atoms, and less number of silicon atoms it offered, rather in turn reduced the, what do you call it, the interface trap charges. Now combining a NMOS and a PMOS, it gave rise to a complementary MOSFET. So this is the background what we have. And to look into the operation and structure of a conventional MOSFET in a different perspective, you see, this is the heart of a MOS. You have the polysilicon, you have the amorphous silicon dioxide, and we have the crystalline silicon, which can be N or P. Well, so why I say this is the heart? Because with the application of a gate voltage, you draw up some charges. Well, these charges, they are the minority carriers as compared to the nature of doping of the substrate. And these two regions, they act as a silicon conduct. And when you give a potential between this and this, then these charges, which are created due to an application of a gate voltage, they are moved from one place to another. We call this one as the source and this as the drain. So this two figures will give you an idea of, rather it is a basic conventional MOS we have seen even in our textbooks. So you see during device operation, so what happens here is that you have a N plus, you have a N plus, and this is P in nature. So since this is P in nature, you will have a depletion region in both sides. Now, if the potential here is higher than this potential, then definitely the depletion region, this will be larger. And not only this, if you apply some voltage here, applying a voltage here means in this gate metal, you are applying a specific number of positive charges. Say for example, so amount of negative charges present beneath the interface, that will be equal to the number of positive charges here. So here, on application of a higher drain voltage as compared to the source, if the depletion width is larger, then definitely these charges, which is highlighted in the yellow color, they are free carriers which are allowed to take part in the conduction from the source to the drain, which we call as the channel. This will reduce this site. So this is basically the charge distribution of a conventional MOSFET. And according to, rather the genesis of current flow in a MOS device, that can be acquainted to the potential which you see here. So when you apply some potential in the gate region, this barrier, this gets reduced, and eventually the electrons start moving from one side to another side. So this is so in other words, if you look into the device physics, there is a difference in the quasi-Fermi potential in the source region as well as in the drain region. And this difference basically causes the electrons to move from one side to another side. So this is a phenomena which is common to all types of MOSFETs or MOS devices. So we are familiar with this type of characteristics. Depending upon the drain to source voltage and the different gate voltages, what we have the characteristics of the MOSFET, something like this, where the demarcation line which you see, if I take any one of the curve, this is basically the pinch off point, after which from the nonlinear region, the curve moves to the saturation region. Sorry. Now, you see, this is the IV characteristics of a MOSFET. Rather, I should say a long channel device characteristics. And uh, these characteristics, which you see here, they operate in the strong inversion region. There are three types of region. One is the strong inversion, another is the moderate inversion, another is the weak inversion. It is how? Because you are giving some voltage at the gate and it is drawing some. If you give a positive voltage, it will draw negative charges at beneath the interface. Okay. So eventually what you are doing is that this region, now the substrate is a different type of semiconductor, doped in a different way, maybe a P-type substrate. So after application of gate voltage, you are making the space near the interface a N-type in nature. And that too, not with doping. And that is with the application of a gate voltage. So basically, you are creating an inversion. So this is also called the inversion layer. So depending upon the strength of the inversion layer, different regions are available. That is the weak inversion, moderate inversion, and the strong inversion. And this is basic, this is the current expression which we have already seen in our various classes. Although this is a very handy expression, but this is an approximate expression derived from Poison's model. Okay, these expression, although they are useful for hand calculations, but they are approximate equations because they are having a number of assumptions. Now, the inversion region, the strong inversion, the weak inversion, if you look into this, we are not able to capture the various inversion region characteristics of the MOSFET. Now, it is only possible when we plot the current in a logarithm scale. Then we see all these regions in a more stronger way. That is, from here, basically, what we see is that even when the MOS device, we are not applying a particular threshold voltage, still a current flows through it. And that is supposed to be the leakage current. One of the reasons of leakage current I will discuss afterwards. So even though if you do not apply a gate voltage, which is stronger than or greater than the threshold voltage, then also a current flows through it, which can be viewed prominently when we look into the characteristics of IV characteristics, plotting the I in the logarithm scale. Now, what is the need for a non-classical approach? Now, before we go further, first it is important to know that how much we have been able to scale down the device. So starting from 1970 or 71, it was 10 micron. And slowly, and this continued. And here, a technological term comes into picture, which is called the technology node. Digital manufacturers, digital IC manufacturers like Intel, IBM, they refer in terms of technology node. So what is this technology node? So if you have a MOSFET here, and these are the contacts to the source and the drain. So this is the pitch of the device. And half pitch of a DRAM is referred to as the technology node. So when we say it's a 45 nanometer technology node, mind it, we are not referring to the length of the channel. We are referring to the half pitch of a MOSFET, and that too a DRAM. And why we take DRAM as a reference? Because in any technology node or any generation of electronics, DRAM is supposed to accommodate the largest amount of transistors as compared to any other application, digital application. So that is why we take the reference of a DRAM. So now, this is a comparison of you can say, the different on a scale. So what we have a fly which we can see, then it comes to the blood cell, then a virus, then a silicon atom, and we are now in this range. So we are in a technology node which is near about 3 to 2 nanometer. So reducing the size of the device as well as reducing the voltage, that is the essence of VLSI. So this is cumulatively, this statement is cumulatively modeled by a single term that is called scaling. So what we see, we have a MOSFET, right? So one idea was to scale it in the horizontal direction. Now to scale it, rather reduce it in the horizontal direction, we have a depletion region. So maintaining everything, if we reduce this in the horizontal direction, then this depletion region will come here. Well, I have not shown the depletion region in the source site, but there will be a depletion region here also. So eventually what will happen, this depletion region will cover up the whole channel space. And this will lower the barrier potential. And even if the gate voltage is not, finite, if it is zero, you're not applying any gate voltage, still a finite amount of current you will observe between the drain and the source. So only reducing it in the horizontal direction that will not solve our purpose. So, when you reduce various short channels effects, for example, channel length modulation, threshold voltage roll off, there are various uh, effects which was not prominent. I should not say those effects were not present when the device was a longer channel device. They were there, but they didn't interfere largely or deeply into the device operation. Now, so one aspect is this. So what we need to do is that not only we have to scale it in this direction, but we have to scale it in the vertical direction also. So the need for scaling in the vertical direction is that now one way is that we reduce the power supply. So once you reduce the power supply, the depletion region that will reduce. So eventually, if you reduce the power supply, then what will happen is the charge, the inversion charge, which is responsible for the drive current of a MOSFET, that will also get reduced. So if I take a simple example, not an example, rather equation of a parallel plate capacitor, which is C is equal to epsilon A by distance between the two plates. So if I reduce D, I can increase the capacitance. And we know C into V is equal to Q. That is the charge. So if we want to retain the same charge, then one hand the voltage is reducing, so we have to increase this capacitance. So increase this capacitance means you have to scale it in the vertical direction also. Now scaling in the vertical direction, making the thickness of the dielectric smaller, it gave to a number of other problems. Like there was a direct tunneling current which was found in the gate region. Now in the gate region, you should not expect any sort of current. So the limitation was existence of a direct tunneling current, which eventually dependent on e to the power the physical thickness. So the solution. So basically, so what we have to work is that, so our intention is to increase this C. So C can be increased because reducing this one, we had a bottleneck. So this quantity or this term has to increase. So there came the use of high K dielectric. Silicon dioxide was previously used, which had a dielectric constant of 3.9 to 4. We need to use something more than that. Now, as far as the gate metal is concerned, what we have polysilicon. Now, so if we want to replace silicon dioxide by some high K material, for example, zinc chromium oxide or hafnium oxide. So what is found that polysilicon and high K material, they are not compatible with each other. Compatible with each other in the sense is that in between polysilicon and high K, So this is your, what you call it as the gate dielectric, and this is the gate metal. In between, another probabilistic interface was formed, which was not desired. So replacing polysilicon, metal gate electrodes came into picture. And you see, this is a trick, because as far as the thickness of the dielectric is concerned, it reached a bottleneck. We cannot reduce it. So there, using a different material other than silicon dioxide reflected the cleverness of research. So which was basically the third thing which I mentioned while discussing the aspects of Moore's law. But replacing silicon dioxide, it was really not acceptable to many of the people. Even these are the newspaper cuttings which was published that time, that how can one replace silicon dioxide, which is supposed to be the heart of a MOSFET. But anyway, around, we have seen devices have been manufactured with high gate dielectric, with metal gate electrodes. Now, as far as short channel devices are concerned, we have several expectations. For example, we need to have a better electrostatic control over the gate region. We have to minimize the short channel effects, increasing the on current, and at the same time, the penetration of the lateral field, that has to be minimized. So one idea came up, which is silicon on insulator. Now, it was based on the idea is that we have the depletion region provided by the drain. We will not extend the depletion region into the body. We'll cut it down. We'll cut it down by a 3D structure, which is basically an oxide region, a SOI structure or SOS structure. SOS stands for silicon on sapphire. Sapphire is a highly polished insulator. And this 3D integration, we got a structure which was known as the double gate structure. You have two gates, gate 1 and gate 2. They are electrically coupled together. And continuing the down, as far as the fabrication is concerned, this double gate, that gave rise to the SOI FinFET structures, which are something like this. They are basically 3D structures. So traditionally, if we see in the bulk technology, we had the P-well process. Sorry, it will be N. This is a typo. We have the N P-well process, N-well process. We have the twin tub technology. All these things were applicable in the fabrication of MOS devices. Now, this twin tub technology, this was an adopted structure of the industry because it released, or rather it eliminated few disadvantages which the N-well and the P-well used to give. So P-well, this is a P-type semiconductor, N-type semiconductor. In this, you develop or you grow a NMOS, and here we grow a PMOS. other structures, other fabrication methods were also tried. That is your trench isolation, where you had a PMOS, you had a NMOS, and in order to isolate these two, an high intensity laser beam was focused here, and then a dielectric material was deposited. So these were the isolation process which was used in conventional MOS structures. Sorry. Now, so this is our conventional MOSFET. And what we basically need, we need a better electrostatic coupling of the gate and the channel region. And not only this, we can increase. Sorry, anyone is saying something? Anyone is saying something? Should I continue?
Oh, no, sir.
Yes, that is so.
Yeah. Anyone is saying something, or should I continue?
You can continue, sir.
Okay, fine. So you see that the motivation is to increase the drain current. Now, this is a very useful, these are a very useful expression. One way of increasing the drain current, what we saw, is that if we can increase the COX by applying a higher value of epsilon oxide. That is the use of high K dielectric. So that was the age of single gate. Now, another way is that what you find in this expression, that the drain current is directly proportional to the mobility. Now, mu0 stands for the low field mobility. Definitely for smaller devices scaled in the nanometric region, this mobility changes. But we can increase this mobility by introducing strain in the silicon channel. And how you can introduce strain, you see here. So this is the silicon substrate, and this is the graded silicon. Now, this is a space where we introduce germanium along with silicon. So it's silicon germanium. Now, after introducing this, the lattice constant, it automatically increases as compared to silicon. Now, if you deposit or grow silicon on top of it, this lattice constant, it will not be same as that of a normal silicon. So we have introduced strain in the silicon channel. So what introduction of strain in silicon channel, this increases the mobility. So one way of increasing the drain current was using strained silicon. So strained silicon along with high K dielectric. This was a very clever idea and a promising idea in the 45 or 90 nanometer technology node. Now, apart from this, if I want to increase this COX, then why don't we use double gate? Now, double gate, it will offer some oxide, COX. This gate will offer some COX. Now, both this oxide capacitance, they are basically parallel. So eventually, the oxide capacitance, it increases because in parallel, the capacitance, it adds up. So we were not satisfied with this also. And instead of two gates, we had a tri-gate structure where we are trying to cover up the silicon channel in three different directions. So this will further enhance the COX and basically enhancing the drain current. So after this, well, mind it, these references are not the year of production or year of invention. I've taken few figures, and that is why the place where I took the figures, I am adding the reference. Now, instead of a tri-gate, the gate metal can be like a coaxial cable surrounding the channel. So this was the evaluation of gate all around or RAB gate. These are the names which were familiar. Another thing is that in this gate all around structure, basically you are, rather what we are doing, we are circumferencing the channel in all the directions to have the largest electrostatic coupling. So apart from this, if we could have a strained channel, then in addition to increasing of COX, we will increase the mobility also. That will give us a further enhancement. Another type of device which came, which are the non-conventional MOS devices, it is the junctionless transistors. And it was invented in 2010 by Professor Collins' group. So here we had no junctions. A MOSFET, you have junctions, the source and the drain. But here, basically, we had no junctions. This had several advantages as well. So this is the cleverness when everything reached to the bottleneck. Applying structural modification and cleverness, we were able to sustain Moore's law. Not only this, instead of one single channel, we can have several channels. So that is referred to as multi-channel gate all-around structures. So these are the reported things, computational as well as fabricated one. And as far as the international roadmap for devices and systems is concerned, which is a body which drives the progress of semiconductor industry. You can see the roadmap, and it is basically this year will be a year of gate all around structures, and which we call as the nano ribbons also. And not only this, a multi-channel will also exist, and not a stacked gate all around structure. Rather, this will end with a stacked gate all around structure. So this is the prediction of IRDS. Now, one property which is the bottleneck, rather one of the properties is the variability. Because in your mind, you are assuming a perfect gate all around structure. But eventually, the thing is that there are various unintentional thing which happens during fabrication. Now, they are out of this, what we are working is the cross-sectional variability. We assume that it is a circular cross-section, what we have seen here, that it is a circular in nature, but eventually it is not. So this is one of the bottleneck where we are stuck. And if it is not a circular, it can possess several structures. It can be elliptical in nature. And a little bit of calculations we did in order to frame the various geometries which are possible from a gate all around MOS structure with and it is characterized by a term which is called the aspect ratio, which is the ratio of the major and the minor axis. So you can see, due to this variability, we can have a spread in the device characteristics. So you see, so this spread computationally, we need to know this, because after fabrication, you are not going to, rather, you start with one value and you reach with another value. So the tolerance, this spread is a measure of the tolerance which has to be computationally verified before fabrication of such structures. Apart from this, you see, this is a structure what we deal with. This is a pure circular structure where the silicon dioxide you see is having a uniform thickness throughout. Here also, you can have an elliptical structure having the silicon dioxide uniform in nature. Well, this may not be true also. You can have a variation in the silicon dioxide as well. You can have, so this can be the periphery of the silicon can be elliptical, but the inside one, which is the channel, it can be a circular. The outside one, it can be a circular one, and the inside channel, it can be elliptical. Now, this gives a non-uniform distribution of silicon dioxide. So this is also one of the causes of variability. Rather, this is also a variability that we have uh, done quite a number of calculations and reported our research in various publications. Another one you see is the source and drain series resistance. Because from the contact, the electron enters into the source and then it enters into the channel. So there is a various variation, either in terms of the dimension or compatibility. So there exists a series resistance in the source as well as the drain side. When devices were long, this was there, I am not saying, but it was not interfering much into our device operation. Now, when devices became shorter and shorter, the source and drain series resistance, this cannot be neglected. As a matter of fact, We did little bit of calculations and validated our results with the experiments. And what we found is that we landed up with an overestimation of nearly about 30% if we didn't consider the source and drain series resistance. So, in order to consider that, rather, if you are modeling or if you are working with a circuit like CMOS, you need to consider all these resistances. Now, this is a little bit of challenge because what we know is the drain current is a function of various parameters, which I mentioned here. Hopefully, you can read it. Now, at the same time, if I take one, say for example, the effective mobility. This effective mobility in turns depend upon the gate to source voltage. Now, VGS or VDS, now there are two things. One is the intrinsic voltage, another is the extrinsic voltage which you are applying from outside. So from here, you see the intrinsic voltage is a function of the voltage which you are applying from outside as well as the drain current. So what happens is that the drain current is a function of the mobility. I'm taking just one example. And in turn, the mobility is a function. I got disconnected due to the cutting of electricity. Can you hear me now? Are we connected now?
Yes, sir.
Yes, sir. Yes.
Yes, sir.
Okay, okay. I'm just at the end of. So can you see this?
Yes, sir. It's visible.
Okay, you can see the full screen also, right?
Yes, yes.
So I think we were discussing about this.
Yes, sir. It's multi-iterative technique.
Yes, yes. So you see, the drain current is a function of all these parameters, and others are also there. But at the same time, if I take one of them, this is also a function of the intrinsic gate to source voltage, which is in turn a function of the drain current. So drain current so what it stands out is drain current is a function of the drain current. So it takes the shape of a transcendental equation. And so you have a number of coupled expressions. They are intercoupled. So a multi-iterative technique that is needed. So with this techniques, we tried to find out various figure of merits. For example, the propagation delay with series resistance, without series resistance. So definitely with series resistance, we had a larger one as compared to a zero series resistance when we worked in a computational mechanism. And this one, as I told you, this is regarding the subthreshold current. And this one, which you see, this is a logarithm scale of the drain current. And the source of this can be attributed to a parasitic or inherent bipolar junction transistor, which is present inside a MOSFET. So you have the N, you have the P, and you have the N. So it is a NPN transistor. So this NPN transistor, we can have an equivalent circuit, something like this. And the base to emitter voltage can be framed something like this. So for long channel devices, this VV is not enough to trigger on the inbuilt BJT, which is present inside a MOSFET. But for shorter channel devices, this VV is strong enough to trigger this bipolar junction transistor. And that is why it lands up with the collector current, which is basically, we call this one as the subthreshold current. So subthreshold means current which is flowing before application of the gate voltage, which is greater than the threshold voltage. So likewise, for different aspect ratio, you can have various subthreshold swing, with the minimum for silicon being restricted to 60 millivolt per decade. And that is due to the material properties of the silicon. So likewise, my God, are we connected?
Yes, sir. Yes, sir. We are connected. Yes, sir.
Okay. The electricity is disturbing a lot. Just 1 minute. Okay. So you see, this is a structure made by gate-all-around devices, a CMOS structure, and these are the voltage transfer characteristics. So there also we have depending upon the various aspect ratios, we can have a spread in these characteristics, which are important to know before device fabrication. Likewise, these are few of the things, computational things we have done with and without the source resistance, and with strained devices and unstrained devices. And as far as interconnects are concerned, you see, the overall signal integrity, because you give an input, you get an output. So it not only depends upon the devices and the circuit which is present in the driver or in the load, but also it depends upon the interconnect. So interconnect, traditionally it was aluminum, then copper came into existence, and these are the various multi-level interconnects which are adopted in the industry, because in the same plane you are not able to adjust devices as well as interconnects. So what happened is that due to scaling, the gate delay that decreased, but delay due to interconnect that went on increasing. So any design is an optimized design where you have to balance the gate delay as well as the interconnect delay. So what I was telling, that traditionally it was aluminum, then copper with low dielectric came into existence. Aluminum has to be removed due to electromigration, because due to high field, when the electron struck the green boundaries, it excluded, it evolved aluminum. So it was rather a material transport. So aluminum was gradually replaced. And for the same reason, when the line width, the dimension becomes further smaller and smaller in the nanometer region, electromigration showed up in copper also. And now people are expecting beyond copper, which is carbon. So copper was supposed to be a 3D conductor. And this you can see, a carbon nanotube is a 1D conductor. And the main advantage which we get is that the electrons travel in the 1D conductor. These 1D conductors have a larger mean free path. Means it can travel without collision. For example, in silicon, in CNT, carbon nanotube, it is nearly about 1 micron. As compared to copper, it is say 40 or 50 nanometer. So we can get a ballistic flow propagation when we speak about 1D conductor, and that too with carbon-based materials. One of the application of this carbon-based material is filling up of this void via. So you have copper here, you have another copper here. Now these two layers has to be connected. So you can use CNT as well instead of copper. It will give you a better speed than copper, as reported in various reports. Now it has been long back that all carbon structure has been realized. So this is the graphene FET, and all these interconnects which you see, the VDD line and everything, they are all made up of carbon. This the world has already seen. So to summarize, as I was emphasizing, that theoretical models and simulators, they are essential for reducing the development time. And this is in line up with IRDS. And undoubtedly, various tools which you see here, they offer technology, computer-aided designs, by which you can play around with, we can model devices. It's true. But in the nanometer region, these tools are pushed to the limits of their applicability. We need to refine them. And here in my group, we play around, rather we try to develop a device circuit co-simulator, because it is not only device, it is not only circuit, but also it has interconnect. So it is an interplay of three of these horizons. So with this, I end my presentation. And if you have any questions, please feel free to ask me.
Hello, sir.
Tell me, please.
It is very interesting, sir. In your last slide, which I have seen that you have connected the interconnection which you have used for this carbon or graphene, sir. How it will be integrated with the CMOS technology? Because both
Yes,
have a different fabrication steps.
yes. They have a different fabrication. In fact, the fabrication steps that increases, that has
Yes.
a different one. You have the silicon, you have the copper, and a more different fabrication, a more number of fabrication steps has to be involved. Both may have a
Yes.
different way of fabrication process. So both of them has to be combined. And that is the reason, what I first said is that I am restricting myself to silicon. Well,
Yes.
these are all in experimental stage. One thing what is true is that the majority of the electronic products which you see, they are consumer electronics. Majority. So, 85 to 90% they are consumer electronics. And consumer electronics, we don't want to spend money. If we see that we are getting the same functionality with one battery instead of two battery, we will purchase the gadget. Okay. Now, a combination, a hybrid with silicon as well as your different interconnects, these are all predictions. Concrete fabrication process, although it is developed, but the cost per chip will rather have not reduced. So for specific application, for example, for all consumer electronics, we use silicon. Okay, that is the base. But for high speed, for example, for specific applications, we move to other materials. For example, for for specific communication, base station receivers, we use high speed devices which are more than silicon, right?
Yes.
So fabrication steps are available, but the cost per chip, which is the fundamental economics of Moore's law, if that is not maintained, people will not buy it. So experimental stage in the research lab, this is there. But
And what
not
about
commercial.
simulation, sir? And what about simulation? If I have to do the simulation in Cadence or somewhere, so how the layout will be generated, sir? Whether the Cadence or Synopsys will provide this, I have not seen that for this interconnection, whether they have given any, apart from any silicon or predefined materials,
No. In that case, what has to be done? You see, I have not included the slides. an electrical equivalent model that has to be incorporated. For example,
Mhm.
in CNT, a single wall CNT, okay, multi-wall CNT, or a graphene interconnect, we have equivalent circuit which consists of inductance, capacitance, and resistance. So if you're using Virtuoso or something like that, then
Mhm.
that equivalent circuit has to be incorporated.
Mhm.
Am I able to clear your doubt?
Yeah, I am getting this. I am getting.
Okay, so even in the LT Spice, a strong simulator is not required. Even in Spice also, which we try to do it in the labs also. Uh, that equivalent circuit that has to be replaced. If you're using CNT, it has an equivalent circuit. It has a resistance, right? Every interconnect, it has a resistance. It has a capacitance. Now, definitely, different types of things come into play. Okay, play in the sense that in that case, if you're speaking about carbon-based graphene or CNT, then quantum resistance come into play. Quantum capacitance come into play. In big capacitance, which you see in the lab, quantum capacitance, we neglect it. It's not there. That it is only the electrostatic capacitance. So different circuit models that exist for CNTs and carbon-based thing. And if you are generating some new type of thing, an equivalent circuit, that has to be generated also. Is this clear?
Yes, sir. I am getting. But still, sir, I have I'm thinking that how the final layout will be generated, because in that layout, I don't think so that a layer will be defined using this CNT. Whether it will be generated
Yes,
from.
yes, yes, yes. Now, in that case, traditional, what you call it, uh, depending upon the aspect
Layers and vias
ratio.
will be used.
Sorry,
Layer and vias will be used, sir.
I'm not getting what?
Traditional material which is defined in the library of any PDK, that will be used.
Yes, yes, yes. Traditional, yeah, that has to be incorporated. Okay, and that is why, this is a separate structure, man, a separate, a field. How to incorporate the layout of this, what you call it, a hybrid structure.
Technologies, hybrid structure.
Exactly. This is a separate where people are, the semiconductor industry, they are adopting people to generate this softwares also, this TCAT tool rather.
Yes, yes.
So I told you, my
Yes.
statement is, what was the
Still,
last
the
statement?
silicon is not replaceable.
No, you see, in the nanometric regime, TCAT tools are pushed to the limits of their applicability. This is a very, very important thing. And your question is addressed here itself. Because TCAT tools, what has been generated, if you speak of the nanometer regime, they are under constant refinement. Okay. And this TCAT, not only TCAT tools, I have taken only TCAT tools, even the layout also, they are also under refinement. So that is why this has not been commercialized. Okay.
Yes, sir. Yes, sir. Thank you, sir.
Thank you, sir, for your insightful and thought-provoking lecture. Your expertise and clarity about the topic fundamentals of nanoscale, MOS devices and circuits will truly enrich our understanding of about the topic. And we are grateful for the time and effort you take it to share your knowledge with the group. Thank you, sir.
Okay, thank you so much for giving me an opportunity to share my little experience and thoughts. So, shall I leave now?
Yes. If anyone any query, then we can ask, you may ask. Otherwise, yes, sir. It was altogether a nice experience today.
Okay, thank you. Thank you. Thank you so much. Thank you.
Thank you. Thank you, sir.
The next separate time.
For the information to all the attendees, please be ready at 3 p.m. The next session is scheduled at 3 p.m., which has been taken by the Professor Nano Kumar last on this topic. And schedule has been shared on the WhatsApp group also. You can check the topic and be returned for 3 p.m. Thank you. Thank you very much for the time.